Okay, hopefully you guys can see my screen now. All right. So I'm actually going to start with a few different things that I hadn't prepared, but I think are going to be worth doing. First of all, the computer's a little slow. Here we go. So first of all, when I think about data, I think about one of the first things I always think about is the structure of the data. And I like to think about the dimensionality of data. And what I mean by that is your data 0-dimensional, 1-dimensional, 2-dimensional, 3 or more dimensional? Wow, my computer is very, very slow right now. This
Okay. Don't feel stressed about that, David. I mean, I would imagine probably actually your computer going slowly is going to ultimately be a benefit because it's going to give people time for stuff to sink in that might not otherwise happen. Okay. So we'll just take it as a blessing and not a curse. So don't feel stressed about that.
So first of all, we'll talk about what a scalar is. A scalar is a 0-dimensional thing, which means it's just a point. It doesn't have length or width. So my first example is we can save, for example, we can save a number, this number 4, we can save as an object, and I'm going to name this object X. And when I run this line of code, you'll notice two things happen. First of all, up here on the upper right, which is called our global environment, it was empty a minute ago, and now it's got X equals 4 up there. And all that tells you is that now there is this object in R's working memory called X, and it represents 4. And the other thing you'll notice down here in the console is that when you run that, it echoes, meaning it shows you which lines of code you've run. Now, of course, as many of you guys probably know, we can create several scalars, and we can, do mathematical operations on them. So when I created Y, now it appears that Y is in the global environment too. When I typed in X times Y, the answer 20 popped up in the console. That's an important distinction. I could have also saved the output of this operation as a new object, and then it would not have popped up in the console. It would have just popped up in the global environment. And just as a little shortcut to show you guys, if I wanted to do both of those at once, if I put the whole line of code in parentheses, it will echo down here with 20, and it will show up in your global environment. These are numbers. I could also save character strings as, oops, I'll think of a new object name for that. Character strings we always represent, we put in quotation marks. So now I have a character string called cat that's also a scalar. The next step up from scalars are vectors. Vectors are 1-dimensional, so vectors have a length but not a width. And the way you create a vector in R is you have to concatenate using this lowercase c function, so concatenate a bunch of things together separated by commas, right? So when I run this line of code, now you'll see that now I have a vector which has 5 things in it. 1:5 means 1, 2, 3, 4, 5. So let's create a couple of these. And now, just like I was performing operations on scalars, I can also perform operations on vectors. I can add them. And when I add them, you'll notice that it goes through element by element. It adds the first 2 elements together, and in the output, that is the sum of the first two elements. Then of course it adds 6 plus 3 is 9, so on and so forth. And of course, just like I did before, I could have saved that output as a vector if I wanted to. I don't want to right now. I'm actually going to create a third vector that has only 3 things in it. And I want to make an important point here. If I try to add vector 1 with vector 3, I get a warning message, and you'll notice that it still gives me output, right? But it also does give me a warning message. So I'm hoping that I'm going to mute myself for about 20 seconds, and hopefully one of you guys can shout out to me what just happened.
So it looks like it like added the first 3 items in those vectors together, and then it started recycling vector 3 to finish adding on to vector 1.
Great, yeah, nice, awesome. That's exactly correct. So what it did is it added the first 3 elements like we saw before, and then when vector 3, the shorter one, ran out, then it went back to the beginning and added 4 to 1, and then 1 to 3. And as Stacy said, this is called recycling, and that's an important thing to keep in mind. By the way, recycling can, obviously we have to be careful of it if we're trying to add 2 things of different lengths, but it can also be a very powerful tool, because if I add a scalar to a vector, you'll notice that that scalar is added to every single element. So that scalar, that 0-dimensional object, is recycled and added to everything until the longer 1, 2 stuff. I want to talk quickly about extracting and subsetting. Let's take a quick look at vector 1 again. Vector 1 contains 5 things, 5 numbers. Now, if I'm interested in what's in the 3rd position of vector 1, I'm going to type in square brackets immediately after the object name and the position that I'm interested in. And this will return the item in that position. If I want more than one thing, I can return a range. For example, 2 through 4, positions 2 through 4. This will tell me everything in that range. And lastly, if I want things that are out of order, I can still have R return those, but we have to do something we have to use a little trick. We're going to concatenate these 3 things again. So if I want 1, 3, and 4, we're going to skip over 2, so I can't use the colon. I'm going to concatenate them. Now you'll see why, hopefully in a few minutes, why we need to concatenate them inside these square brackets, and we can't just list them separated by commas. Before we talk about that, though, I want to talk a little bit about functions. So first of all, let's use the mean function. Anytime you use a function in R, you type in the function name immediately followed by parentheses. So if we wanted to take the mean of everything in vector 1, we could put the vector in there inside the parentheses, meaning that it's an input to the function, and it will return us the mean. So in other words, what the mean function just did is it wrote 5 things and gave us an output of only 1 thing. So it turned a vector into a scalar. Functions can do all sorts of different things in R. For example, the sine function, if we use the sine function on vector 1, some trigonometric function, it's going to go element by element and calculate the sine for each of those 5 different things. So those are 2 very different things. Another cool function is the class function, class of vector 1. This is of class numeric. Before I told you we created a character string. And so that character string is a class character, so that has very different properties in numbers. Let's talk a little bit about missing values. I'm going to go ahead and I'm going to replace what's in the third position of vector 1 with an NA. Now what an NA means is in R, this is the way R thinks about missing values. So I can almost guarantee that if you continue on in research, you're going to have experiments that fail for some reason, and you're going to end up with some missing values. And so you'll have to learn how to work with those in your data set. So now let's take another look at vector 1. Now it's the same exact vector, but of course the third position is no longer 5, it's been replaced by NA, so it's missing. Now if we use those same two functions on this vector, you'll see that when we take the mean of vector 1, it doesn't calculate it. And the reason for that is because anytime an NA, a missing value, is an input to a function, by default, the function says, okay, something's missing, something's wrong, I can't calculate it, so I'm not going to return anything. Of course, if we did the same thing with sine, now what this does is this can still calculate all of them except for the third one, which is missing. So that will return missing. Now, of course, in almost all scenarios, when we take the mean of a vector that contains a couple of missing values, we still want the mean. We just want it to ignore the missing values. And so there is a way that we can do that. And in order to do that, I'm going to talk about a little bit more about functions. Specifically, I'm going to talk about arguments of functions. You can think about arguments as being inputs to a function. So a really handy way to find out more about a function is to use the help, the help information, I guess the help page for a function. So you type in either help and then the function name, or equivalently, you can type in question mark function name. And now for the first time, we'll be looking down in the lower right of this screen. Hopefully you guys can see that. So here it's going to tell us all about the mean function, everything we could possibly want to know. Now I want to direct your attention to where it says usage. Under usage, you can see that it says the function name, and then right here, hopefully you guys can see where I'm highlighting, it says mean, and then in parentheses, x, comma, trim equals 0, comma, na.rm equals false, comma. Now, each of those three things, which are separated by commas, are an argument to this function. And the argument that we're interested in right now is this na.rm argument. We can override the default value, which is false, and tell it that, yes, we do want to remove missing values.
So David, is that RM saying remove?
Yeah, so what this is saying is, do you want to remove missing values? And the default is false, saying no, keep them in. But of course, we're going to override that right now.
Okay, thanks.
And so now this will give us the mean of those four numbers. So before we move on to anything else, I just want to say a couple more things about arguments, right? So you'll notice in here, if we look, let's look down here at the help page for the mean function again. X is the first argument. So X is the thing that you want to take the mean of. Now you'll notice that these other two arguments are followed by an equal sign and something else. Equals 0 for trim, equals false for na.rm. Now what that means is that these arguments have default values. So the default value for trim is 0, meaning don't trim off anything from the tails of this distribution. We want to include everything. The default to na.rm, of course, as we know now, is false, meaning don't remove missing values from this calculation. Now, often a lot of the functions you are going to use, you'll have to provide more than one input to. And when you do that, there's a few ways you can do that. If you always provide arguments in the same exact order that they're written and you don't skip anything, you don't have to name them. You can just list them right out. In our scenario, we didn't modify the trim argument. We wanted to go straight to the na.rm argument. So in that case, since we skipped over something, we had to provide the argument name. And just to drive that point home, I'll provide all the arguments totally out of order. But since I named them, R will still know how to handle that. So does anybody have questions on functions or arguments before we move on? Because I think this is really important for Okay, cool. By the way, if you guys have questions at any point, please stop me. I'm more than happy to answer them as we go. So, okay. All right. So we've talked about scalars, which are zero-dimensional. And we've talked about vectors, which have a length but no width, so they're one-dimensional. Now we're going to talk about the next step up. Matrices are two-dimensional. So I'm going to create a matrix. And I'll leave it to you guys to, on your own, you can get help on the matrix function by doing that and figuring out exactly how to create a matrix. But for right now, I'm going to create a matrix that contains the numbers 1 through 24. And I'm going to make there be 4 columns. And I'm going to create this, but I also want to see what it looks like. So I'm going to put this whole line of code in parentheses so that it will also echo back in my console when I run it. So this matrix has the numbers 1 through 24 in it, and it has 4 columns. So of course, 24 divided by 4 is 6. So it must also have 6 rows. Now, of course, a matrix has rows and columns. So it's got a length and a width, which makes it two-dimensional. I can find out the number of columns in this matrix by doing that. I can find out the number of rows of this matrix by doing that. I can find out the dimensions of this matrix by doing that, so on and so forth. There's all these different operations I can do on matrices. Many of them I can also do on vectors. The mean of all these numbers, of course, is 12.5. The numbers 1 through 24. I could take the sign of matrix 1. And interestingly enough, this returns a matrix of the same dimensions, but now each element is now the sign of the original element. So let's talk, before we move on to data frames, I want to talk about extracting and subsetting from matrices. So in order to extract and subset values from matrices, we use a method very, very similar to how we did it with vectors, those square brackets. Now, the only difference is that with matrices, we have to specify 2 dimensions now instead of just 1 dimension. And the way we specify those dimensions is we first specify the row number, then we put a comma, and then we specify the column number. So let's take a quick look at matrix 1 again. I want to extract this number 17. I want to extract this number 17 from the matrix. So the way I would do that, first I'll provide the row number, which is 5, and then I will provide the column number, which is 3. So again, just one more time, I'll restate that because it's really important. When you extract from a 2-dimensional object, you first provide the row and then the column, and they're separated by a comma. Now, all the same things that we did before with vectors, we can do here too. Maybe I want rows 1 through 3 and columns 3 through 4. That's totally legitimate, and that will just give me that one little rectangle inside there. I could also get things out of order. Let's see, maybe I want just the first row, and I want columns 1 and 3. So that will give me those two observations that are both from row 1 that occur in column 1 and 3. Two more quick things about extracting and subsetting from matrices. If I wanted it to return all the rows and only one column, for example, column 3, instead of writing 1 through 6, I can just leave it blank, and R knows to interpret that as if I wanted everything. So that's that entire row, the third column. And the last point I want to make is that lowercase c function, that concatenate function, is really handy not only for returning things out of order, it's also really handy for returning things in a different order. For example, if I wanted the fourth column first and then columns 1 through 3, I could use that, and it would now return a matrix with the last column first followed by the others in order. Oh, and by the way, hopefully now you guys have realized why, when I was subsetting from that vector, and I say I wanted things in positions 2 and 3, this would not work because R, let's give it a shot. R thinks that vector 1 is a two-dimensional object. It thinks that I'm asking for row 2, column 3. And of course, vector 1 is not a two-dimensional object. It only has length. So that's why we need to concatenate that to reduce it to the one dimension that we want. Okay. I'm going to move on to data frames. I'm going to assume that there aren't any questions unless you guys stop me. Feel free to unmute yourself or write something in the chat if you want to as well. So let's talk about data frames. So I'm going to create a data frame. I'm going to do that using the data.frame function. I'm going to create a data frame with 3 columns. The first column will be named A, and it will just contain the numbers 1 through 10. The second column will have a bunch of random numbers in it. Oops. And then maybe we'll have a third column with some other random numbers in it. So if I put this all in parentheses, again, it will do both. It will create it in the global environment and it will echo in my console so I can look at it. So here's what that data frame looks like. I'm not going to go through all the rigmarole of extracting and subsetting again, because I can assure you that it's the same exact thing that we would do for matrices. We would again use rows and columns to extract different things. Instead, I want to focus on some things that are unique to data frames. First of all, when you're working with data frames, there's an additional way that we can extract and subset things when we're talking specifically about columns, when we're doing column operations. And the way we do that is with this $ symbol. This $ is what we use to refer to a column by its name. So df1 $A will return column A. df1 $B times df1 $C will give me the product of columns B and C. And of course, this is each of these columns. You can think of each of these columns as just being a one-dimensional vector, just having length. So what this is it's the same thing as multiplying 2 vectors. It goes through element by element. It multiplies the first 2 things then the second two things. So it returns something of the same length that you started with. Of course, I can save the output of this as a new column. I can create a new column in my data frame that is the result of some column operation I perform. And now if I look at our data frame again, I can see that it's got a column V now, which is the product of B and C. I will mention one other thing about extracting and subsetting from data frames, and this actually is true for any object. So far, we've extracted things by their position. For example, here's what's in the third row, fourth column. But I can also extract things by their name. Column B, the column name of B, of course, is B. So if I wanted to extract column B, that would be equivalent to this. And of course, this will show you that, yes, indeed, that is equivalent in every single position. By the way, these trues and falses, if we check the class of this vector here that we created, the class of this vector, all those trues, is a new class called logical. So logical is trues and falses, another class of data. I'm going to copy and paste this now down here. And
I have a quick question, David.
Yep.
When you're referencing columns by the name of the column, can you, oh shoot, what'd you call it? So can you subset doing that too? So like, could you do B to D and it'll know to do those in order, or do you have to then do it by position if you're trying to get that subset of columns in order?
Yeah, that's a great question. You can do everything that we did with position by names. The only constraint is that you can't mix and match. You have to, if you're going to use names, you have to stay consistent and use names for all the columns you're trying to get at. I'll just quickly address a little workaround to that. If for whatever reason you do want to mix and match positions, which are numbers, and names, which are character strings, you could use this handy function called the which function. So which, where do these column names equal B? And so instead of typing in the name B, this will return the position too. So if I wanted to combine positions with names, this is a handy way to do it. That kind of skips ahead a little bit. A couple of things I should have mentioned first are, of course, the call names function. This returns a vector of column names, which are of class character. And the other thing I did here that I didn't really mention is that in order to create this logical vector, I say, tell me where these column names equal B. And it's important to use two equal signs in this case. If you just use one equal sign is pretty much the equivalent of the assignment operator, which is this little arrow we've been using. So just to make one more point about logical vectors, the double equal sign will test for where that equality occurs. And then when you put this logical vector inside a which function, the which function returns the positions of any truths, okay? All right. Now, moving on, I can save this logical vector I created. I can save this as a new column in my data frame. So now my data frame has a bunch of numeric columns, and it has a column of class logical. And this is an important distinction to make between matrices and data frames. Data frames can contain columns that have different types of classes in them, whereas matrices, everything in a matrix has to be of the same class. For example, all numeric or all characters, you can have a matrix full of characters, full of logical vectors. But data frames can have columns of different classes, not rows. You can't mix and match rows, but columns you can have of different classes. Okay, so I realize that's a lot in a short amount of time. I'm hoping I can talk briefly about functions, writing your own functions and lists before we start talking about multivariate stuff.
You just said, David, that you can't mix class in rows, but that last data frame in row 1, the last column isn't numeric, it's actually logical.
In this data frame, you mean?
Yeah, the one that's shown down on the console.
So, yeah, so I guess I wasn't too clear about that. So everything within a column is the same class. I think I may have misspoke. So everything within a column is the same class. But you can have columns of different classes within a data frame. Okay. All right. I'm gonna jump ahead to some stuff. Here we go. Let's talk about writing your own functions. Writing your own functions is a really great skill to have in your toolbox. Here's a very basic function. I'll first talk about the structure of writing your own function. So actually, I'll just use that example. So in order to write your own function, first you think of a name for it. It can be anything. Then you type in function. And then inside of just regular old round parentheses, you can put what the argument to your function, what variable you want your function to have as an input. And then inside curly brackets, so again, we call this the argument. This is the argument to this function you're making. And then inside of these curly brackets is the body of the function. And it's the body of the function that says, okay, every time we get this input to this function, this is what we're going to do to it. We're going to square it and add 1. So I'm going to create this function, and I'm going to pass the number 7 to this function. So it's going to, in this case, when I pass the number 7 to this function, 7 is x. So what it's going to do is it's going to square it and then add 1. And of course, that's 50. So again, to write a function, you think of, and this can be anything you want to name it. You think of a name for your argument or your variable, and that goes between parentheses. And then inside of the curly brackets, you put the body of the function. This is the stuff you want to do to these arguments. So a slightly more complex function would be something that does multiple steps. We still have only one input, x, but now we're going to do multiple things to this x. As you can see here, first what we're going to do is the same exact thing we did before. We'll square x and add 1. Then we're going to save the output of that as a variable y. In the next line of code, we subtract 3 from this y that we just created, save that as z, and then finally, in the last step, we will square z. So this is a 3-step operation. Every step, we create a new object internally within the function. These new things won't show up in your global environment because they're internal to the function. Now, of course, I could have done this all in one step if I copied and pasted that and put that in place of y and then put parentheses around it and put it there, but it's kind of neat to see things in 3 steps. Often it can be a little easier to follow. So let's create this second function, and now we'll pass the number 3 to that. So let's see what happens. So first, it squared 3 and added 1 to create 10. So now y equals 10. Then it subtracts 3 from 10, giving z, which is 7. And then it squares 7 to give us 49. So that's good. Now I want to take it another step. We're going to write a function of more than one variable. So this function that I'm writing here has 3 arguments, 3 inputs. I'm going to give them all a different name, and just like we learned before, I separate them all with commas. So what this does is in the body of the function, it's going to return, it's going to first add the first 2 arguments, x and y, create a new variable called p. In the next line, we're going to do something totally unrelated that doesn't involve p at all. We're going to subtract z from x and create q. This is totally random, but hopefully it will illustrate my point. And then finally, we're going to multiply these two things, p and q, that we created, create something named r, and then we're going to tell r that we want r to return r. Sorry, that is confusing, but we want the software to return this object r. Now these functions that we write work just like any other function that R already knows in its memory, like the mean function, the sine function. We always have to provide arguments in order unless we name them. So in this case, when we run this function on 2, 4, and 3, it's going to use 2 as x, 4 as y, and 3 as z. And I'm not going to go through this one like I did the last one. I'll just have to hope you guys will believe me when I say that if you go through all this math, then you indeed do get -6 when you provide these 3 arguments in that order. While I'm on this function, I'm going to make one other point. You'll notice here something new I did. I wrote return r in the last line of this function. I'm not going to include this, and I'm going to rerun this function, recreate this function with without that line of code in the body. And now when I run the function, you'll notice it doesn't return anything. The reason for that is just like how we code normally. If you save something as a variable in the last step, it'll remember it in the global environment, but it won't echo down here. So we've created R, this function did create R, but just like normal coding, if we wanted R to appear in our console, we'd have to actually write R or return R. Both are identical. So the point I'm trying to make is R will always return the last thing a function asks for, unless you use the assignment operator to save it as a new variable. And that's just like in our normal coding.
So, David,
yeah.
if you scroll up in your global environment, there's an object called R now because you ran that?
Nope, I don't think so. So that's a good point, Lucas. Anytime your function creates things internally, it doesn't pop up in your global environment. It's only in that temporary working memory of the function.
Is that true even if you include the return R?
Yes, Stacy, it is. The only way I could get the output to pop up in the global environment is if I save my output of the function as an object, right? By the way, another alternative to what I just did, instead of writing R here or return R, both of which do the same thing, I could have just not saved this output as anything, and then it would pop up. right? And again, this is just like our normal coding, where if we type in some operation and don't save it as any new output, it'll just pop up down here. So hopefully by now I've convinced you that anything you put into the body of a function is just like normal coding. It's just like anything you do outside of a function. It's just that when it's inside of a function, it's looking for arguments that you pass to the function from when you wrote it. Okay, so
I have a question on functions.
Yeah. Yep.
It's mostly about syntax. So I know like in Python, it's really sensitive to how many spaces you have and how things are indented. Is that the case for these curly braces and then how you've indented, say, your first 3 lines on function 3?
No, that's another good question. No, it's not. I wouldn't have to indent. I could put as many spaces as I want. It doesn't matter. The one thing I do like to be kind of consistent about, I like to keep my code kind of pretty because, for example, if I had no space there, does this mean p is less than negative x plus y, or does it mean p, we're assigning this value to p, you know? So just to make that very clear, I'll try to keep my code pretty, but no. And also one other thing, Stacy, is that if I wanted to, I could combine all these operations onto one row if I separated them with semicolons. So this is also a very viable alternative to what that function did. All right. I now want to make the claim that we can use functions for things other than numbers. We can provide entire data frames as inputs to functions. So I'm going to create a new data frame that has 2 columns, A and B. And now, excuse me, I'm going to write a function that multiplies these 2 columns together. So let's take a look at this function. This x here, in my mind, I want this x to be a data frame with a column A and a column B. And in the body of the function, it's going to be looking for this column A from this data frame. And it's also going to be looking for a column B from this data frame to multiply that A by. If our data frame doesn't have those 2 columns that are named exactly that, this function won't work. But fortunately, the data frame I created does. So when I perform this operation, this function on this data frame, it's going to multiply columns A and B together, and the output will be the product. Now, of course, this is great, but what if we wanted to create a new column containing this information in our original data frame? Well, we just do that just as if we were normally coding. We would save it using the assignment operator as a new column in our data frame. Now, take a minute and look at this function right here. Based on what we talked about earlier with functions, why is this function not really sufficient for what we want to do? So remember from before that when we save something using the assignment operator within the body of the function, it's not going to return, right? It'll calculate it, but it won't return it. So in this case, we actually have to, like before, we have to specify what do we want x to return. Well, do we want x to return column C? I mean, sure, but really what we want is we want it to return the whole data frame, right? This would be really handy. So that's what I'm going to do. I'm going to type, instead of returning this thing, I'm going to have it return the whole data frame. So now we can see here that it did indeed, it returned the whole data frame with this new column. All right. I want to, so yeah, I'm going to move on now to lists. Is this helpful for people, or Yeah, okay. Okay, all right, let's talk, that's just stuff from before. So, well, thank you, Stacy. All right, so lists. Lists to me for a long time were this kind of mysterious object in R that I really didn't know about and I didn't really have the desire to learn about. But first of all, I guarantee that if I can wrap my head around lists, I guarantee you can too. And second of all, I want to make a plea to you guys. My plea is I really hope you will spend the time learning how to become comfortable working with lists, because if you are ever in the position where you have many data frames that are all structured in the same way, you know, a lot of us would copy and paste our code, go through and painstakingly change all the names. And it's so much easier and so much less prone to making an error if you save everything within the same list and just apply a function to each list element all at once. And I'm going to give you guys an example of that. I'm not going to go through too much about lists right now. Hopefully I'll have a chance to do that with you guys maybe in the future, or I'm sure you could figure it out on your own too. But I'll show you, I'll just quickly give you an example of this to wet your whistle a little bit. So I'm going to create 3 data frames, and let's take a look at one of them. Each of these data frames contain the same 3 columns, some plot identification number, and then a carbon concentration and a nitrogen concentration. Now, each of these data frames contains values that are a little bit different, but the overall structure is the same. They all have the same 3 columns that represent the same 3 things. And so what I want to do to all 3 of these is I want to create a 4th column for the carbon-nitrogen ratio. And so, of course, I could do this the way we've been doing it. I could do this for each data frame separately, or I'm going to save them all in a list. So here's my list 1, which is a list containing 3 elements: df1, df2, and df3 in that order. So I'll just quickly show you what this list looks like. List element 1 is df1. Then, of course, element 2 is df2, and so on.
Quick question
This
on
lapply function is, sorry?
Quick question on lists. Can you mix the data structure of the items in your list, or should they all be the same type? I guess if you're performing a function, you'd want them to all be similar.
Yeah, lists, you can save anything to a list. The structure of each element does not have to be the same at all. If you're trying to perform the same operation on a bunch of different things, that's when, of course, it's important for them all to be the same. But of course, Stacy, the next step above and beyond this would be to, you know, maybe you have a list of metadata, for example, plot level measurements, like location and vegetation type and so on. And then you have another data frame that contains more detailed information, like all these nutrient concentrations. And then you have 2 lists side by side that have elements that kind of match up, but the data within each of them is very different. And there are ways to mix and to combine elements of each of those. That's something for another day though. So this lapply function here stands for list apply. So it's going to apply a function across each list element. So let's do something like n row. So I'm going to apply the n row function to each list element. So if I run this, it's going to calculate how many rows are in each of those data frames. Now, of course, that's great, but let's get back to our real problem here, which is we want to create this new carbon-nitrogen ratio column, right? So here's the function I'm going to write. It's gonna look for a carbon column from this data frame X that is going to be the input. and it's going to divide it by a nitrogen column from the same data frame, create a new column, and then of course we'll return the whole data frame. So we know from before that this will work on individual data frames, but if I apply it to this list, and remember, each list element is a data frame with a carbon and a nitrogen column, it will return each data frame with this new column calculated. I know I didn't get too crazy into lists right now, but I would really encourage you guys to check them out on your own if you could see yourself, you know, having to manipulate lots of data frames all at once. Okay, so I'm going to move on now to talk about some multivariate stuff. You guys want to take a minute break, or yeah, let's take like a couple minute break, maybe grab some water.
And David, you have to read the comments at this point. Everyone needs to read the comments.
How do I read the comments?
Oh, I don't know.
Chat.
You could do R. You could find the comments on the chat. Yeah.
Oh, wow. That sounds like all the Lucas Bernhardts are chiming in.
Lucas Bernhardts are happy, real, fake, and otherwise. That was really cool.
Thank you, guys.
Thank
Great.
you for doing that. I know, like, Maddie and I were recently talking about some of her abiotic data that I have, because my lab collected data, like we're collaborating on a project, and I'm like, I really know that I should try to pull these together into R and not be bad and just like copy paste in Excel, but oh my God, you just fixed it for me. And then the not real but actual Lucas and I were talking one day about like how you often are doing the same things to the same like Excel sheets all the time, right? When you get something off of your, you gave the example of carbon and nitrogen analyzer. So this is awesome, because actually we can probably really all start streamlining the way we do our data analysis, which was kind of the point, right? So that was cool.
Yeah, cool. That's awesome. I'd love to, if you guys run into any questions, I'd love to be a part of that process too.
Yeah, reducing error in the long run is I think one really nice plus of using R instead of trying to remember how you did calculations in Excel for years.
Yeah, you're right. I mean, R's so prone to, it's so sensitive to typos. I mean, it's case sensitive and whatnot. So any little mistake, anything you forget to change can really throw off your data. So,
David, when you're making data sets, do you use Excel and import it, or you just do it all entering it in R?
So in my lab, we collect data on a Campbell Scientific data logger, and I download that data to a computer, and it's in a .dat format. It's basically comma separated, and I'll just import that right into R and manipulate it all into R without going through Excel. It's for visually seeing what is going on with the data. I would definitely recommend maybe on a subset of your data working through a problem, maybe in Excel, or certainly at first with R, working through just one data frame at once, getting all the steps exactly how you want them in R. And then as you become more comfortable, you can start to scale up and do things in a more efficient way.
But it sounds like maybe in general, as far as just like, knowing that your data you can reproduce what you've done, and that that it's all in an R script, like using comma separated values instead of Excel formats are good, because you can't really mess it up as much, right?
Yeah, I mean, R also has, there's great packages for uploading data from Excel spreadsheets instead of CSVs too. But yeah, I mean, if you have a code that works in R, it's a lot more efficient time-wise and whatnot.
Yeah.
Do it that way. Yeah.
I'm just, I love this, because, I'm here from the future to tell all of you guys that you're going to do the same calculations on the same type of data a lot of times, like you're going to have to transform that ppms of whatever, nitrogen or CO2 or whatever, into like something meaningful per gram dry soil, like, I don't know, 1 million times probably by the time you retire. So if you have created the R script to do it, you'll save yourself time and headache probably in the long run. So
Cool.
that was cool.
Thank you. All right.
Yeah, thank you.
Ready to jump into part 2?
I am. I don't know about you guys. Yeah. Cool.
Okay. I don't think this will take quite as long as part one. So, all right, I wanted to start by talking about a few different types of distance measures. First one is Euclidean distance, and I think we're all hopefully familiar with this one. Euclidean distance is basically the absolute distance between 2 points in space. And of course, you guys know that if we have 2 points on an XY plane, we would calculate the distance between them using the Pythagorean theorem, right? So it's equal to the x component distance squared plus the y component distance squared, and then you take the square root of that. So that's just the Pythagorean theorem. Now, when we have data in higher dimensions, three and 4 and more dimensions, it's the same exact formula. It's just that there's more terms in here. So here would be the Euclidean distance for 3-dimensional data. So I'm going to make a little plot just to. It's always helpful to. I think it's always helpful to think about statistical analyses and mathematical operations graphically. It really helps you understand them. So I made a few graphs here that will hopefully help. Let me. This popped up in a new screen for me, so I'm going to share this screen with you guys, and then we can go back. So here's a 3-dimensional graph. You can see 3 points in space here. Now, Euclidean distance is just the absolute distance between them, which we calculate again using Pythagorean theorem. So that's kind of the plain vanilla, plain vanilla type of data distance. I'm gonna share my screen again with you guys. Now for community data, which I think is what most of you guys are working with, Euclidean distance may not be entirely appropriate because in large part due to zeros. And I'm gonna explain that, why I make that claim right now. So let's look at, we're gonna look at, hopefully you guys can see the lower right, this plot that I just made, lower right portion of my screen again. So we're gonna look at, there we go, oops. There we go. So this graph shows the distribution of 3 species over an elevation gradient, right? So species 1 occurs a lot at about 100 meters above sea level, and then at 150 meters, this third species peaks, and then of course, 2 seems to like higher elevations around 250 to 350 meters above sea level. So I guess one thing I think you'll agree with me on is that for species 2, there's almost no species 2 up around 500 meters, and there's also almost no species 2 down around 100 meters. So if we were sampling plots at both of those elevations, and we found zeros for species 2 at both of those elevations in both of those plots, if we were to use Euclidean distance, those 2 plots would be identical, right? They both have zeros. So they'd be exactly identical. So there's a lot of useful, there are many useful distance measures that essentially will not call 2 plots that have that have 0 for the same species, will not call them similar. So the most common one, Bray-Curtis, is one I would probably suggest using for this. I'm going to go run through a calculation on how this works. Let's first create just another made up data frame. I'm going to create a matrix where the rows rows are plots and the columns are species. I think we're all familiar with looking at those. Now, the way that Bray-Curtis distance works, let's just calculate Bray-Curtis on between plots 1 and 2. So what we're going to do is we're going to go through column by column for plot 1 and 2, and we're going to look for the overlap. So you see here that species 1, there's 3 of them in plot 1 and 4 of them in plot 2. So they overlap by 3, right? They have in common between both of those plots, there's 3 species 1. So we have a 3 for species 1. We have a 0 here. There's no overlap because plot 2 doesn't have any. And then of course here we have 2, an overlap of 2, because they both have 2. So in order to calculate Bray-Curtis distance, what we do is we sum up the overlap, what they have in common. So 3 plus 0 plus 2. And then we divide by the total sum. So the total sum of species of observations in plot 1 is 15, and the total from plot 2 is 6, so we divide by the total. Now, the one thing I didn't mention is that this overlap here, these 5 species that are in common, we multiply that by 2, and the reason we do that is because in the denominator, this 15 plus 6 takes into account that overlap. That those 5 species here plus those 5 species here. So we multiply that by 2 in the numerator because we've essentially included it twice in the denominator as well. So that's the formula. And if I were to just calculate that, we would get how similar they are. So when we subtract it from 1, we get how different they are. Right? Okay, so of course
David?
we can calculate, yeah.
Real quick, I don't want this to like detract from anything, but I've always been confused about row names in R.
Yeah.
So plot 1 through 4 there are not, it's not a separate column in your data frame, correct?
That's correct, yeah. Those are the row names of my matrix.
How does R treat those? If you don't reference them, are they wholly ignored by R when you're doing these calculations?
Yeah, names are not names of anything. Matrix column or row names, data frame column row names. You can even have a vector that has names of each individual element. But when you perform an operation on them, the names are totally ignored. The only reason names are important is if you're trying to keep track of where things are, or if you're trying to extract or subset, you can use names instead of positions.
Cool, thank you.
So of course we can calculate an entire distance dissimilarity matrix using that same calculation and looking at every single different pairwise comparison that can occur between those plots. And I'm sure you guys have seen these too, but just looking at an example here. So this is what we call a distance matrix or a dissimilarity matrix. And it shows the distances between, and of course this is Bray-Curtis, so this shows the Bray-Curtis dissimilarity between each pairwise comparison. So plot 1 and plot 2 is about 0.5, it has a dissimilarity index of about 0.5. Plots 1 and 3 is about 0.6. Now you'll notice 2 things. First of all, you'll notice that down the diagonal of this matrix are all zeros. And that's because plot 1 and when you compare plot 1 with plot 1, they're the exact same thing. So they're not dissimilar at all. And the other thing you'll notice is that this is what we call a symmetrical matrix, meaning that if we were to flip this matrix over its diagonal, it would be the exact same thing. And that also makes sense because when we compare plot 1 and plot 2, that's the same exact thing as comparing plot 2 and plot 1. It's just the opposite order. So Bray-Curtis is a great choice for community data. Jacquard is very, very similar. I'm not going to go through the calculation, but it's also a great choice for community data. And it can kind of be used pretty much interchangeably, I think. I know that most of you guys probably don't have presence-absence data, but I want to go through this one example of presence-absence distance right now, and you'll see why I'm doing this at the end in a few minutes. So first of all, presence-absence data is instead of abundance, where we have, or frequency, we have the number of species, or the biomass, or some measured value. Presence absence data only contains ones and zeros. So if a species is present, then there's a 1 in that position, and if it's absent, then there's a 0. I'm gonna skip over this so that we can just quickly look at an example. Here's a matrix filled with presence absence data. So we can see here that species 1 is present in plots 1, 2, and 3, but absent from plot 4. So this is what I mean by a presence absence data frame. So just going back up here, a couple things I wanted to point out. First of all, there's this thing called Beal smoothing, which is somewhat commonly used for presence absence distance matrices, and I just want to encourage you guys not to use this if you have presence absence data, because it's kind of like a band-aid fix. It takes a distance measure that's designed for count data and sort of modifies it a little bit to be used for presence absence. And I would suggest to you guys to use a distance measure that was specifically designed for presence absence data. So there's Sorensen's is a popular one, and that's a really great one. And it's basically the same calculation as Jacquard that I mentioned before. And I'm going to go through an example of a different one here called so-called missioner, which is kind of another popular one. This is actually a similarity measure, not a distance one. But since like Bray-Curtis, it ranges from 0 to 1. So anytime you have a similarity index and you want to calculate dissimilarity, all you have to do is subtract it from 1. So we're going to calculate the so-called missioner similarity index for between plots 1 and 2. So what this does is this looks for, so for species 1, we can see that species 1 is present in both plots 1 and 2. We can see that both species 2 and 3 is absent in one and present in the other. So in other words, when something is present in both plots or absent in both plots, that means that the plot is similar. If something is absent in one and present in the other, that means that the plots are different. So we're going to add up how many times they match and divide by the total species. So that's what we do here. So between plots 1 and 2, we have 1 match out of 3 total. So that gives us a similarity of 1/3. And so of course we could go ahead and calculate, like we did before, the entire distance matrix. It's going to look something like this. And in this case, oops, I made a mistake. Since this is a similarity index, the diagonals are going to have 1s instead of 0s because plots are similar. Because this is a similarity index. Now, back to the point I made above, why am I going through this rigmarole with you guys if you don't have presence absence data? And the reason for it is because you may have categorical variables that you'll need to include in your distance calculations. So what I mean by that, so far we've calculated distances based on purely quantitative data, counts, frequencies, so on and so forth. But let's look at another example data frame. Here's a data frame, and each plot, we've classified its soil type, right? So we have all these different soil types. So how do we calculate a distance matrix based on these soil types? Well, of course, you can't calculate something numeric from all these categorical values, But if we do a slight modification to this data, we're going to create new columns that act as dummy variables. And I'm just gonna go ahead here and calculate them and show you and kind of talk about what I mean. So, oops, that's way too, let's, so what I did is I took this data frame that lists all the plots and their soil types, and I expanded it and I created a bunch of new columns that act as dummy variables. So if we look at which plots were clay loam, well, none of them except for 6. Which plots were loamy sand? Well, it looks like plots 1, 8, and 9, excuse me, are loamy sand, and so on and so forth. So zeros represent things that aren't true, and ones represent things that are true. So we can, essentially the point I'm trying to make is that you can expand, you can calculate distance matrices for categorical variables if you use these dummy variables. And the way you'll do that is using presence, absence, distances, like the ones we talked about before. And of course, you may want to mix and match. Maybe you have some quantitative variables and some categorical ones. So you could calculate a Bray-Curtis distance and then calculate a presence-absence distance for your categorical variables, and then average them to get an overall distance between plots. So there's a lot of options you can do with distance. All right, so I'm gonna, I have a very brief ordination example. Is everybody feeling pretty good about distance measures? I'm gonna turn my video back on because I think my housemate's off for conference call. Cool. All right. I'm gonna just roll right into this. It's not that long, and then we'll take maybe another few-minute break before Nate gets going. So I basically just want to go over very basic ordination. So ordination is plotting our data in multidimensional space. I'm going to go back up to one of our previous examples. Let's look at this matrix that we use for the Bray-Curtis distance. So we have 4 plots and 3 species. If I wanted to plot this data in what we call species space, there are 3 species, so this would be 3-dimensional data. The x-axis could represent species 1, y-axis could represent species 2, so on and so forth. And then each of these points would have, plot 1 would have a point in space with these coordinates, 3, 10, 2. So going back to ordination, I want to go through a 3-dimensional example with you guys. Let's say that we collect data and then we make a plot, we make an ordination. We plot these all in species space. So each point represents a plot. So here we go. Let's create a plot. I'm going to share this with you guys so you can see it. Okay, so oops, sorry. In this example, the axes aren't species. The axes are soil nutrients. So we have the x-axis is carbon, and the y-axis is nitrogen, and then the z-axis, the 3rd dimension, is phosphorus. So let's take a minute to look at this cloud of points. So each point is a plot that corresponds to a particular carbon and nitrogen and phosphorus value. And when we plotted them in this three-dimensional, I guess we can call it nutrient space, it looks like it's pretty spread out here, but if we keep spinning it, it looks like it kind of flattens out. We'll keep spinning it all different orientations. Wow, here it's really small, right? So if you look at it, you're kind of like looking right down the thing and it looks really small. So you can kind of think of this as like a flat piece of bacon or a flat football or something. So it's long, but it's kind of flat. So it's long in this direction, and then a little bit less long in this direction, and then pretty darn flat if we look at it this way. So when we perform ordination on our data, we can reduce our data that's in many high dimensions, it could be more than 3, down to just a couple dimensions. And the way we do that is we try to capture where the maximum variability is occurring in our data. What I mean by that is if we made a plot that looked like this, we're gonna miss out on most of the story that our data tell because it's all spread out in this direction, right? So our first job when we perform ordination, and I'm going through an example of principal components analysis, which is like the plain vanilla ordination type, I guess, the most basic, but really great to help visualize. So our first job is to determine where the most variability in our data are. Which axis contains the most variability in our data? So we rotated it and we were pretty confident that we found where it is. So I'm just going to go ahead and draw a line through it. So now you can see that line that I just drew goes through where that most variability occurs in our data, right? So what this line is this line is principal components axis 1. This is the line that captures most of the variability in our data. And in case you're ever interested, this line, what this line really is it's the eigenvector from the covariance matrix of the data. Anyway, now our next job is to calculate or find where the second axis is, where the next most variability happens in our data. So let's rotate this around our first axis, and you can see, remember it's kind of flat, but it's wide here. And it flattens out if you look at it from the other direction. So I think that this is the next axis. Now the constraint that we have is all of our principal components axes have to be perpendicular or orthogonal to each other. So when we place this next axis, we can shoot it off in any direction, but it's got to be perpendicular to our first axis. So I'm gonna draw that in here. So here's our second axis, and you can see that it goes through, it's perpendicular to the first one, and it goes through that width where that data is pretty wide. And then of course we can go in and fill in the last principal components axis too. There's only one spot that it can possibly be because it's got to be perpendicular to both. So there it is, and it captures very, very little variability in our data. So we see that this first axis captures a lot of variability. The second one's kind of helpful too, because our data is still spread out in this direction, but the third axis doesn't really tell us much. There's not a lot of action happening around there. So I'm going to share my R screen with you guys again. All right, so now that we've found where the PCA axes are, all I'm going to do is I'm going to make a plot, and instead of using our original axes, I'm going to use PCA axis 1 as the x-axis and PCA axis 2 on the y-axis. And this is what that's going to look like. So here's our data And all I've done is I've changed the basis. So instead of axes being X, Y, and Z, now PCA axis 1 is X and PCA axis 2 is Z. And just quickly, I'm going to go back to the graph I just made and rotate it so that you can see where this is coming from. So PCA 1 is X and PCA 2 is Z. So this cloud of points that we can see looking down from above on it is what this graph is. So in this one graph here, we've captured almost all of the variability in our data, but now it's in 2 dimensions and it's a little easier to work with. And just as a word of caution, often when you graph data from ordinations like this, it's going to rescale them. So you can, from this graph, it's still pretty clear to see most of the variability is right here, and there's only a little bit in this direction. Often when you plot data from ordinations, it's going to rescale it. So here you can see that the y-axis scale is decreased, so now it looks pretty spread out on the y-axis. But if you actually look at the coordinates, you can still see that this has a lot more variability. Often people even go as far as to rescale it so that it's not in terms of the absolute data at all. Now it's in terms of standard deviations. So it's the same exact graph, but instead of being from -100 to 100, now it's all in terms of standard deviations, how far away from the mean you are. So yeah, so that's all I have on ordination. Nate's going to talk about a very different type of ordination that follows some of these things a little bit, but also is very different. So why don't we take like 3 or 4 minutes and then come back for Nate. Yeah.
All right. Is everyone seeing my screen? Cool. Okay. Sweet. So, yeah, so this is kind of, I'm going to work through the script here. So first off are just some packages for people who have done ordination stuff with R. You're probably familiar with vegan. So that's a package that a lot of people use for ordination, specifically ecology related stuff. And I guess briefly, so packages kind of build on the base functionality of R. People have kind of written these packages to give you some easier ways of using R. And so a lot of them are really useful and really commonly used. So we're going to use ggplot2, which a lot of people are probably familiar with, to do some plotting. And then vegan has some 3D functionality too for visualization. So we'll use that as well. And I'm going to work with this dune data set, which is some Dutch dune meadow plots. So we're looking, they're basically meadow ecosystems, and we'll be looking at the plant communities in those ecosystems. And there's some environmental variables about what kind of management practices are used in those areas, and a little bit of stuff about the soils. So a quick review of what kind of David showed us. So we could start off talking about a one-dimensional space, right? And so we could say that plot 1 has 0 of this species 1, right? So we'll just say that we're doing count data. So we'll say there's 0 of species 1 in plot 1. And in plot 2, there are 3 of species 1. And in plot 3, there are 6 of species 1, right? So it'd be really simple. Then we could add an extra dimension to that. So we see plot 1 still has 0 of species 1, but now we're adding our second dimension, and that is the abundance of species 2. And so in plot 1, there are 5 of species 2. Plot 2, we still have 3 of species 1, but now we have 3 of species 2 as well. And so you can see how we can add dimensionality to these things. And if we added a third species to that plot, then we would have 3 dimensions. And you can see up here, this is kind of specifying the coordinates, right? So right now we have 3 coordinates, an X, a Y, and a Z, but we could imagine how we could continue to add additional dimensions to this. We can't really visualize beyond that third dimension, but in practicality, we could add some. And so this is kind of useful. You can look at the proximity of plots 1 and 2, and that tells us a little bit about the species composition in these plots. So it looks like plot 1 and plot 2 have more of a similar species composition than plot 1 does with plot 3, right? And so this is called plots in species space, which David mentioned, and it's kind of the most common way of ordinating things. You'll see that the most. And so species space, basically meaning that we're defining the space, our axes are these species, right? So we're in a species space, and what do we have in the space? In the species space, we have plots. So that's referred to as plots in species space. But David showed an example. You could also have plots in environmental space. So if we had environmental data on these plots, for instance, of B horizon pH, B horizon nitrogen, and B horizon calcium, we could also have plots in an environmental space. And similarly, you could have species in trait space, which is pretty cool. You don't see as much of that, but just to kind of make you aware of how all the different possibilities for ordinating things. So we could see that species 1 here seems to have kind of small petal lengths, large sepal lengths, and smaller petal widths, right? So we can ordinate like that. So for this presentation, I'm going to talk about plots in species space because it's, I think, one of the easier ways to think about these, and it's really common. So we have 3 dimensions here, but we could continue to add dimensions, right? And so let's look at the data set that we're going to use. It's this dune data set. So we can see that the rows here, these are the plots. So this is plot 1 here, and in plot 1 we have Acamil, Achilla millifolium. There's one of those, and it looks like there aren't any other plants found there. And in plot 2, there's 3 counts of Achilla millifolium, and there's a couple other species there, right? So let's look at the dimensions of dune. So we see that it reports that there are 20 rows and 30 columns in this. So can anybody guess how many dimensions we're looking at? So in our species space, how many dimensions will our full data set have?
20.
Yeah, so 20 will be our number of plots, and our dimensions will be 30. We've got 30 species. So if we look at this, so species 1, species 2, species 3, we're going to get up to 30 dimensions. And within those 30 dimensions, we're going to locate 20 different plots within that space. So I'll just kind of cut to the chase of what NMDS is going to do for us. So here's kind of a kind of end result NMDS, right? And so what we're seeing here, these circles are plots, and the colors of the plots tell the management type of that area. So each one of these circles is a meadow ecosystem that they collected plants from. And these 4-letter words are the actual species themselves. So with these plots, we see a little cluster of plots here, right, that are all the same management type. And we see these 3 plots appear to have very similar species composition within them. And we see the species around them, and so that means that those species tend to associate with those plots. You would expect in those plots there's probably a high abundance of those species. And we see this vector here labeled A1, and that's the depth of the A1 soil horizon. And so in this area of the ordination where that vector is pointing to, there are larger A1 values. So there's deeper A1 horizons in that area. So these species here are associated with deep A1 horizons, and these plots here are associated with deep A1 horizons. And alternatively, up in this other area, these are associated with shallower A1 horizons. So those plots tend to have shallower A1 horizons, and the species tend to be associated with shallower A1 horizons. And these are kind of general trends, right? It doesn't mean that this plot over here can't have the deepest A1 horizon, but you're kind of using some regression techniques, and we'll talk about how we actually get the direction and the magnitude of that environmental vector. So you can produce a figure like this with other ordination techniques like PCA, and there are a bunch of different options for ordinating. So why would we use NMDS to create this ordination? One of the benefits is that it doesn't have an assumption of linear relationships between variables, and there commonly aren't linear relationships with community data, especially abundance. We have a lot of zeros, and so that's a really nice aspect of it. It allows us to use any distance measure, and so PCA is restricted to just Euclidean distance. And so in our NMDS, we'll be able to use something more appropriate like Bray-Curtis that David mentioned. And then this also uses ranked distances, which we'll talk about a little bit more, but ranked distances is what makes this method non-metric. And so something like Kruskal-Wallis that also uses ranked distances, it's useful for some of these kind of non-linear relationships, and it helps us describe environmental variables and species. So the disadvantages, which from what I've read, really aren't as much of disadvantages as they used to be. One is it's computationally intensive, but with improved computing, that's not so much of an issue. And then the other one historically has also been finding local minima, which we'll talk a little bit. So the NMDS tries to find a solution, and there's the possibility that the solution that it finds is only if you picture yourself in kind of a mountain landscape and it finds some summit, that might only be the local summit, and there's some larger peak somewhere else that this algorithm didn't find. But with improved algorithms, that concern is also kind of reduced. So it's a great tool for community data. I think it's kind of the go-to ordination technique for community abundance data. And so for the overall process of how we're gonna run this, we're gonna start off, so we're working in a 30-dimensional space. So we're gonna start off with our 30 dimensions, and we're gonna tell the NMDS how many dimensions do we want for our solution. And commonly you'll select like from 1 dimension up to 6 dimensions and see what the different options are that we could use. And we'll choose the one that is most appropriate for us. And then you would move on to plotting what those results look like. So let's look at actually running an NMDS. So we have 30 dimensions right now, right? And David showed us a distance matrix already. And so what we did here was we used this vegan function, vegdist, and we're calculating the distances between plots, right? So on our rows here, here's plot 3, and here's plot 1 here. So this value here is comparing plot 3 and plot 1. What is the distance between those points in 30-dimensional space? And it's giving us a Bray-Curtis distance, and the Bray-Curtis distance is a proportional distance. It kind of tells us how different are these compared to how different they could potentially be. And so Bray-Curtis goes from 0 to 1. 1 would be these plots are as different as they could possibly be, and 0 is these plots are exactly the same. So when we look here, this value is comparing plot 3 to plot 1, and this value here is comparing plot 3 to plot 2. And so what this would tell us here is that plot 3 is more similar to plot 2 than plot 3 is to plot 1, because this value here, this distance is smaller, right? So, and what the ranked part of NMDS is right now we have 30-dimensional space and we're using Bray-Curtis distance, but now we're going to assign ranks to these distances rather than the distances being absolute distances. So let's look at this row here, 4. So this is plot 4, and we're going to compare plot 4 to plot 1, plot 2, and plot 3. So the plot that plot 4 is most similar to is plot 3 with a value of 0.27. And so if we were doing ranked distances, that would be number 1. That is the closest plot to plot 3. So we're kind of just pretending right now that only this row here 4 exists. We're kind of ignoring the rest of our matrix, our distance matrix. So if we're assigning rank distance to just these 3 values, this would be rank 1, this is the closest. This would be ranked 2, that's the second closest. And this here would be rank 3, it's the third closest plot. And in reality, we would apply that to our whole distance matrix here. The closest value would be 1, and it would go all the way, whatever the last comparison is, would be whatever that number is. So that's really useful. And 30-dimensional space is really informative. It tells us kind of like if we're looking at this 3-dimensional space, so if we're looking at our full dimension, it tells us it's kind of our best description of the species composition in a plot, and it's also the best description of what plots are similar to each other. But 30-dimensional space is enormous and impossible to kind of visualize that. So we need to reduce that down into an interpretable number of dimensions, and that's usually 2 or 3 dimensions. So NMDS gives us a way of reducing down our number of dimensions. And what happens is when you reduce the number of dimensions from 30 down to say 1, 2, 3, things like that, you can only represent that relationship so well in that reduced number of dimensions. And the information that's lost during that process is what's called stress. And we'll get more into what exactly stress is, but it's kind of how much information was lost when we tried to reduce the dimensions. So let's look at actually running an NMDS in R. So we're gonna save our results in this thing called NMDS Dune1. So you just come up with a name, whatever you want. And then we'll use this vegan function called meta-MDS. Here we name our data set. So we're using the Dune data set. We name our distance, which is Bray-Curtis distance. And then we name the number of dimensions, which is the K value here. So this is going to be a 1-dimensional solution. And try is the number of times that you want this NMDS to try to find a solution to this. So it keeps doing the same process over and over and seeing if it can find a better solution. And it gives you an option to auto-transform your data, which can be a good idea. And I didn't go over transforming your data before this, but you should look at the skew and kurtosis and things like that in your data and consider transforming. Log transformations can be really useful. So definitely look into that. And later on in this presentation, I'll talk about some options that Vegan has for doing transformations in a really convenient way. So let's run this 1-dimensional solution. And we see here, this is the amount of stress. So we talked about stress as kind of how much information was lost during this process, right? And we're looking for stress values to be 0.20 or lower, preferably lower. And we're seeing a lot of high values here. And we'll see that this runs 250 times because we told it to try 250 times. And so this thing ran 250 times. And at the end, it said no convergence, which basically means it's not finding a stable solution. It's trying to reconfigure these plots in a way that maintains that original relationship. And it's unable to do that with 1 dimension. And you can imagine going from 30 dimensions to 1 dimension is really kind of unrealistic, really challenging, unless you had a very simple kind of data set. So that's unsuccessful. And let's just run this whole thing. So we're going to run solutions ranging from 1 to 6 dimensions. And this runs fairly quick. This Dune data set isn't huge, but I could imagine with some of the data sets that you're working with like microbial stuff, this could take quite a while, especially a 6-dimensional solution. So, so we'll see. Let's look at the 3-dimensional solution. So now if we run the 3-dimensional solution again, we can see these values are much smaller, looking at 0.07, 0.07. And if we go kind of towards the end, we see a lot of values that are similar, whereas in the other one, the values were all high and they were ranging. It was finding different solutions each time, but we're seeing pretty consistent stress values around 0.076 seems to be popping up a lot, 0.07. So it keeps finding the same solution, and that gives you some confidence that your NMDS it's deciding to configure your plots in the same ways each time, and it's a reliable way of placing those. And
Nate, I have a quick question.
yep.
Does it pick out of your 250 runs the one with the least amount of stress to then give you that figure at the end, or does it pick the last one that it ran?
Yeah, so it's looking for, I believe it's looking for kind of the lowest thing that it keeps finding. So it wants to keep finding the same solution. And I think you could potentially have a low value, but if it can't keep finding that, then that would likely be an issue. It's not, that's kind of the convergence thing. It wants a lot of its attempts to end up kind of at that same summit or valley, however you want to think about it. But yeah, that's converging, or it keeps finding the same solution. So, but yeah, it's trying to do that with the lowest stress solution. So let's look at a stress plot, and we'll get kind of a, where did that go? Whoa. Sorry. Okay, so here's our stress plot, right? And so what we're looking at here is on the x-axis is our observed dissimilarity, and that was in our 30-dimensional space, right? So the x-axis is our Bray-Curtis distance. And on the y-axis is our final solution, our ordination distance. And your ordination distance is always measured in Euclidean distance, because when we look at an ordination solution, we look and interpret things in Euclidean distance. So when two plots look close to each other, we want that to mean that they're similar to each other. So our ordination distance is always using Euclidean distance. And what we want to happen is that when our original 30-dimensional Bray-Curtis distance is small, it should also be small for our ordination distance, right? And so let me see if I can.
Hey, can I ask a quick question about that?
Yeah.
So the Euclidean distance that we're using here is the Euclidean distance between those points on the NMDS plot, right? It's not, is that right?
Yeah, exactly. Yep. So the y-axis, that's the Euclidean distance on our NMDS. Yep. And the x-axis is that 30-dimensional Bray-Curtis distance, but ranked, right? So it's not that absolute distance, it's that ranked distance. And so let's see if I can draw on this thing. So we're comparing these things, right? And we have a rank. So we could put rank 1 here. And so that would be our Bray-Curtis distance. This is our smallest Bray-Curtis distance. It was rank 1, like we did that example where we ranked things. Well, we also want that to be our smallest ordination Euclidean distance, right? And then our second distance should be 2. And we want that to be our second smallest Bray-Curtis distance and also our second smallest Euclidean distance in our NMDS solution. And then we want 3 to be here, and it creates this monotonic line, this straight line, where when Bray-Curtis distance increases, Euclidean distance should increase in our NMDS solution. But unfortunately, when you reduce dimensions, you lose a little bit of ability to represent things. So what if 4 was here? It's increased in Bray-Curtis distance, but it's decreased in our Euclidean distance, right? And so that means that it's not being represented in the right place. And stress is kind of a measure of how far off. We would need 4 to be up there to be in the correct monotonic location. And so stress is kind of a sum of all the points. Every time it has to move a point, it's like, this isn't actually in the right place. We need to move that, we need to move this. That adds up and creates stress in your solution. So that's how stress is calculated. And let's see here. So then we ran six NMDSs, right? So let's look at what these solutions came out to. So on our x-axis here, this is the number of dimensions in our solution. So we see our one-dimensional solution, and on our y-axis is the amount of stress. Our one-dimensional solution has a lot of stress, which makes sense when you go from 30 dimensions to 1 dimension. that one dimension is going to have a lot of stress. As you add dimensions, you decrease the stress, and that also makes sense. Once you got to 30 dimensions, you'd be able to perfectly represent this thing again, and you'd have no stress. So now our job is deciding what dimensional solution is the best to use. When we add more dimensions, it creates difficulty interpreting things. If we had a dimension or a solution that was still in 6 dimensions, we still can't really look at that and understand it. So that's not really useful. But we also don't want a ton of stress because that means our solution is somewhat unreliable. So the rule for this is a vector of the stress. So this number here is the 1 dimension. If we look at dimension 1, it's up around 0.27 stress. So we see that here. And then this next one is our 2-dimensional solution. 0.118 is the stress. And so we continue to add dimensions. We start at 1 dimension and we look at that. And we say, if we add 1 dimension, do we significantly reduce the amount of stress? Are we really improving our visualization of this? And the rule of thumb is that if you decrease the stress by 0.05, then it's worthwhile to add another dimension to your solution. So let's look at the first. We start off at 1 dimension. We've got 0.276. Now, if we add 1 dimension, we decrease the stress by much more than 0.05. So that's a worthwhile decrease, or that's a worthwhile to increase the dimensions there. Now we're at 2 dimensions. Should we change to 3 dimensions? Well, do we decrease the stress by 0.05 or more? And in this case, we don't. It would need to be 0.068 or lower for us to add that 3rd dimension. So we'll stay at 2 dimensions in this solution. And so this stuff's all kind of saved in your NMDS output. So we originally called this thing NMDS 2 Dune. And when you put that $sign there, like David was showing us, the class of these things are a little more complicated. Like, I'll show you the class. So the class of an NMDS Dune 2 is a meta MDS. So it's not one that David showed us. It's a little more complicated, but it has information stored in it. And one of the pieces of information it has stored is the stress. And so we can run the stress there. And it tells us it's 0.118. So what does that mean? So we can evaluate our stress. Stress from 0.05 and lower is excellent. I've never seen an ordination published that has stress that low. 0.05 to 0.1, they call good. I don't know if I've ever seen one that low either, but that would be really great. That means that your solution is really doing a great job representing those distances and patterns in your data that were originally described in 30 dimensions. And then from 0.1 to 0.2 is probably more likely where you find yourself. And you start to have a little bit of trouble relying on this information as you get up to 0.2. Beyond 0.2 is considered kind of unreliable. So with values approaching 0.2, you're starting to be a little suspicious when 2 points are close to each other. Were they really supposed to be close to each other in 30 dimensions, or is that kind of misleading? So you should treat those solutions with a little bit of caution when they start getting up towards 0.2.
I have a quick question.
Yep.
Just going back to where you checked the class type of your solution.
Yeah.
How do you look and see what sort of information is held within that class type?
Yeah, so I don't know too much about that meta MDS class type, but if we went to NMDS Dune 2 and then did our $sign, it gives us all these options of what is stored in here. And so a lot of these I don't know what they mean, but I can tell you we'll look at what points are and we'll look at what species are. And there's a lot of other information stored in there that I'm sure you can find some documentation on.
Cool.
Would you be able to get all of what those are in the help for NMDS?
Yeah.
Is that where we would go for that? Okay.
Yeah, exactly. Like David showed us, if we did meta MDS, that would bring up. Oh, actually, good question. Oh, because it's sorry.
I forgot to talk about the structure function, str. That's always really handy. That'll show you everything that's stored in that objective.
Yeah, nice. Yeah. Yeah, so we can look at the structure, and a lot of it, is pretty complicated, but we will use the points and we will use the species in a little
You
bit.
can see that structure information over in the global environment too, right? In RStudio? Is that correct?
I believe you can, yeah, if you expand these.
Yeah.
Yeah.
Okay.
Yep. So now we've run an NMDS and we've decided what solution is best for us. So now we'd be on to kind of creating our visual of this. And what I'm going to do is I'm going to proceed with a 3-dimensional solution rather than the 2-dimensional solution. Based on the stress, we should choose the 2-dimensional solution, but it's a little bit more interesting for plotting, and it's pretty common, especially with complex data sets, to need to use a 3-dimensional solution. So it's good to know how that works. So when we start plotting, here's a reminder of what our visual is going to look like. The first thing to add are the actual plots themselves, which Vegan refers to as sites. And so that is stored within your NMDS results because it's essential. That's how it decided what the stress was, right? The whole process was to decide where should we position all of these plots relative to each other to maintain the original kind of structure of our data set. So we can look at the site scores here, and it's really pretty simple. So if we did NMDS Dune 3 points and ran that, this shows, here's plot 1, and these are the coordinates for plot 1. So we've got our 3 different dimensions. And the code here is just a little bit of formatting stuff. We're kind of extracting scores and putting them into a data frame. And I'll share this with all of you so you can see how that works. But we're just getting out those site scores so that we know how to plot those. And then we'll move on to getting our species scores. And so the species scores are also stored within our NMDS solution. And the way that the species scores are determined is by using weighted averaging. And so we see that this plot here has the highest NMDS 1 score, right? It's about 1.1 or something like that. And so that heavily weights the NMDS axis. This plot here weights that NMDS axis 1 heavily. And so we use its axis score as a weight. So the weighting for this plot is 1.1, let's say. And so you'd look at the species in here. So if we were trying to determine the species score for this Juncardi, this Juncus species, we would say how much abundance of this species is in this plot, and we'd multiply it by the weight of that plot, that 1.1. And then we'd go to the next plot, we'd say this plot here has about a weight of maybe 1.05 or something like that. How much Juncus is in that plot, and multiply that by that 1.05. You'd keep doing that for all the plots, and then you divide that by your total abundance of that species, and it ends up giving you an NMDS axis score. And then you would do that for the axis 2, and then you'd have your 2 dimensions, and you could represent it on this figure. So that's how species scores are determined. And in just kind of a more basic way, it's associated with the correlation. So this part of these high NMDS axis 1 scores are correlated with plots that have a lot of this species, right? And so that's how that species score gets out there.
Nate, may I ask you a question?
Yeah.
So it sounds like, as with every statistical test, with this would be especially susceptible to outliers in your data because of that kind of weighting. So what kind of things do you suggest people do to look at their data before they do a test like an NMDS to try to figure out if they have outliers before they begin? Yeah.
So I guess you definitely want to look at your skew and kurtosis and things like that. And you can do, you know, log transformation or whatever transformation improves those values. Then there's also, which I didn't talk about, commonly you reduce rare species in your data set. So species that appear in less than 5% of your plots, you generally remove those from the data set. And because rare species are so common, you know, there's only a few like really abundant species. For my master's work, I think I went from like 230 species down to like 80 species. When you remove species that are only within 5% or more of your plots. So you can lose a lot of species through that. But some of the outlier stuff can be reduced a little bit by using these ranked distances. So that can help alleviate some of those issues as well. Yeah.
Thanks. Interesting. Yeah, we were having a kind of offline chat about that 5% or less thing. I think maybe our group, we should actually look into, I don't think you'll tend to do that in microbial data sets. I think you'd lose a lot.
Yeah.
And so, I mean, we have these just very, very skewed distributions. I mean, I know all species abundance are, but like extra super skewed to be very quantitative about it. So I think we should maybe look into that and think more about that for our type of data. But
yeah,
I think I just kind of want to, I'll be aware, like data exploration is important as well. Yeah.
Totally. Yeah. David, do you have anything to add to that?
I mean, what Nate said is accurate about skew and kurtosis and removing rare species. I'm not familiar with microbial stuff, so I can try to think about that a little bit. Maybe if I come up with anything, I'll let you know.
Yeah.
So we did a trial. Oh, sorry.
Go ahead, Stacey.
RJ up at work had done a trial where he was looking into this, and for one of our data sets, we had 15,000 ASVs, and when we removed 5% or things that were present in less than 5% of the samples or something, it removed like 14,000 of those ASVs. So definitely important to look into that for our type of data.
Yeah, I think especially people who have taken Rich Smith's class. We work with Bruce McCune, the McCune and Grace, what is it called? Analysis of ecological data or something like that. Maybe that's the name of the class, I forget. But anyways, it seems like Bruce McCune's interpretation of doing some of this stuff is different than the guy, his name's Yari Oksanen, and he made vegan. And I think he's kind of another one of the authorities on, you know, running ordinations. And they seem to have a little bit of different opinion on some of these things. I don't see as many people talking about removing the rare species in the vegan world, but Bruce McCune's definitely a proponent of that. So, yeah.
Right. It's a good reminder that statistics is also an experiment.
Yeah, totally.
Yeah. All right. Thanks. I'll let you keep going. I appreciate you digressing for that.
Yeah. Right. So, okay. So we calculate our species scores here, and this is just the same thing. We're just kind of extracting those species scores and putting them in a nice little data frame that's going to make it easier for plotting in the future. And then there's the environmental vectors. And so we just have one environmental vector with this data set. It's this A1, which is the depth of the A1 horizon. And so there's both magnitude and direction for this. The direction points to where the A1 horizons are largest. And then there's a length associated with this vector. If we had other environmental vectors, you'd see that they'd have different lengths. And the length is associated with the correlation. And so the way that this is done is you run a linear model. The response is the A1 horizon, and the predictors are both the NMDS1 and NMDS2. And so that gives you some coefficients for the NMDS1 and 2. Those end up determining the direction of the arrow, and the strength of the correlation is the length of the arrow. So once again, to me, and I've talked to David about this too, those that and the weighted averaging thing, they're kind of associated. They're kind of different calculations, but it's basically saying our plots over here generally have deeper A1 horizons, and our plots over here, so it's kind of a correlation between your NMDS axis scores and the plots, the value of the A1 plots, or the values of the A1 value in those plots. So, and a note on environmental variables, they can be calculated. There are a lot of different environmental variables, and the units can be very different. You could be looking at pH, you could have like canopy cover, you could have a concentration of something. And so some of your values might be 0.1, but that might be a really large value for that measure, and the other value might be in the thousands, but that might be really low. And so a common way to deal with that is to standardize by the max value. So if we're looking at soil calcium, the highest soil calcium value would be 1, and everything else would be below that, because you would divide every value by that max value, right? And so that's a good way to get everything between 0 and 1, and now the scale of these environmental variables are all comparable to each other. And Vegan has a really cool function here using this deco stand. So I encourage you to look at the documentation on that. Is a really simple way. You just say method we want to relativize by max. The alternative for doing that using R requires much more coding, and so that's really useful. And I encourage you to also use that on your species data too, to check out some of the options using that. And so this end fit function here, this is just doing that linear model that we talked about, using the linear model to determine the direction of that arrow and using the correlation to calculate the distance of that arrow. And we're doing the same stuff here. We're just kind of extracting those values and putting them into a data frame. And we can also, we see the permutations here, 999. And so using our permutations, we can calculate a p-value for these things. So we see that this A1 value, this is an important environmental variable. If we had more environmental variables, we might see that some aren't very important. And we have our 3 dimensions associated with these. So the plotting is using ggplot, and so I'll share my code with you. It takes a little bit to get familiar with the ggplot syntax, but we've extracted all these things. We have our species scores, we have our site scores, and we have an environmental variable. So we have all the pieces now extracted into some nice tables, and they're kind of ready to use. And so, first we plot these sites. It's kind of the bare bones of this thing. That's what our NMDS originally was trying to figure out, where should we put these plots relative to each other. And you'll see here, we're looking at axis 1 and axis 2, right? Now we're using a 3-dimensional solution. And so once you go through and create your plots for axis 1 and 2, you would go back through and you could change this value here to a 3, and make sure you change, you have other instances of it, but change those, and then you can create graphs for 1 verse 2, 1 verse 3, 2 verse 3. And obviously there's some kind of compromise by looking at these things individually. You're not seeing it all in one moving piece, but we will look at a 3-dimensional option. But I will note that ggplot has a lot of functionality for making things visually appealing and just look, lots of options for changing the visuals of things. And so despite only being able to look at 2 dimensions at a time, sometimes it's as good as looking at 3 dimensions at a time. So then we add the species scores onto this, and then finally we add our environmental variable onto that. And so if we look at this here, we're seeing different management types. And so BF here in the reddish is biological farming. So remember, we're looking at meadow plots. So BF is this biological farming. HF is hobby farming. So that's the green here. The bluish is nature conservation management. And we see that those are quite a bit different than the other ones. And then standard farming kind of up here. And so we're seeing kind of clustering. Things are clustering by the colors. So we're seeing that the management type does impact the species composition of these sites. But there's definitely some overlap. I mean, overlap here with the red and the green and the purple here. So let's look at a three-dimensional solution. Oh, and one other thing I want to mention that's really important, I probably should have mentioned it earlier, is that NMDS axes are really different than PCA, like David mentioned. So PCA, we had this cloud of data, and then he skewered the bacon, right, through the most variation, and then he went orthogonal to that in the second most variation. Well, NMDS axes are totally random, and they're basically meaningless. We told NMDS, we want a one-dimensional solution, we want a two-dimensional solution, we want a three-dimensional solution. And you tell it how many dimensions, and then it just tries to figure out where to put these points to maintain that original kind of relationships and structures in our 30-dimensional solution. So these axes they don't mean anything. And you see commonly with PCAs and some other ordinations, they'll say the amount of variation explained by an axis. And you can see how when David skewered through that, that explained a large amount of the variation, and you could describe that. With NMDS, Bruce McCune does use the amount of variance explained by NMDS axes, but Vegan doesn't give you any options for calculating that, and the developer of it is pretty emphatic that these axes are meaningless and you should never be reporting the amount of variance explained by an NMDS axis. So that's really important. And yeah. So let's look at the three-dimensional solution. And so this is using Vegan 3D. So now we have a three-dimensional representation, and we see that a lot of that overlap that we were seeing before is not actually what it looked like. So this biological farming, this is this green here. It doesn't have a ellipse around it because I think you need more than 3 points for them to put an ellipse. But it looked like we had overlap in our two-dimensional solution. But when we look at this in the third dimension, we see that there's not actually overlap there. There's actually very little overlap between these two, which standard farming and hobby farming. It looks like there's just kind of 1 point that actually overlaps there. So those communities are probably somewhat different. We see that the biological or the nature management is quite different than everything else. And so using 3 dimensions can be really useful at seeing exactly what's going on. But I will note that when you have lots, like we have 4 categories for our management. When you have lots of different categories, like I'm dealing with different forest types and lots of different, like we have 100 or up to 200 plots that we're looking at, these 3D ordinations can get so chaotic that it's really not any better than looking at a two-dimensional thing, because you can hardly tell what's going on. And the last thing will just be, there's this RGL widget function, which you can't run in our studio, but for those of you who have worked with R Markdown, this is a really nice format where you can publish this to an HTML file very easily. And with that, we can actually zoom in to these things, zoom in, zoom out, and it's a nice, easy, publishable script too, so we can kind of see exactly what's going on. We see that there's really just this 1 point here is overlapping, but the rest of that community, they're in similar ordination spaces, but they appear to be somewhat different potentially. So yeah, that's about what I have. So hopefully that was useful. Does anyone have any questions?
In that 3-dimensional figure you just showed us with the ellipses, were those like confidence intervals, or are they?
Yeah, sorry, I should have explained that. Yeah, so those are 95% confidence intervals. Yeah.
Okay.
Yeah.
Cool. And can it not create those in 2-dimensional space for some reason, or?
You can come up with those. Yeah. So yeah, that's a good question. So I was using This plot here is created using ggplot.
Mm-hmm.
And so there's a lot of benefits to ggplot, just how versatile it is. And there's a ton of documentation. And you can basically make the plots look however you want them, if you can figure it out. But Vegan offers their own kind of graphing options, which aren't as versatile, but everything's kind of contained nicely. Like you see, before when we had to extract all these scores into different data tables and get them all ready to go to plug them into Vegan, or to plug into ggplot.
Yeah.
When you're working with Vegan, they're kind of like, they're compatible because you produced these NMDSs in Vegan, and now if you use the Vegan graphics options, it kind of knows how to interpret these meta MDS structures and things like that. So there's a lot less that you have to provide it, but there's some limitation to how much manipulation of those graphics that you can do. And so that's what you're seeing here is it's a little bit simpler to tell it what to do. And you can do that for 2 dimensions, and you can create those 95% confidence interval ellipses with that. Yeah.
Well,
Yeah.
thanks. What other questions people have?
I don't have any right now, but I'm sure once I take a look at this, I will have some.
Yeah, I'll send you guys this code, and if anyone has any NMDS questions, just let me know.
So I actually do have another one for you, kind of based on the fact that you don't have any measure of how important the axes are. And so while you can create a p-value around saying like the depth of the A horizon was really important for explaining distribution of species, how do I know if, even though I know that that's important to the data, how do I know that the data are actually, like that's actually important at all? If really in reality, somehow I could figure out, well, this axis isn't actually, this is explaining 2% of the variance, but that 2% is really well explained by A horizon. Well, I probably want to write that paper differently than I want to write one where I know that that axis is explaining 90% of the variance. So is there, I mean, I know this was an NMDS lesson and I don't want to put you on the spot, but I guess I am, so sorry, you can be like, pass. But, you know, is there another better tool that we could use that we can get variance on those axes?
Yeah, so there are ways of getting the variance explained by the axes, and it is explained, I don't think in the Vegan documentation, but if you get into some of the darker corners of forums out there, you'll find this guy, Jari Oksanen, and he does explain how to calculate that, and he basically says if you have a reviewer who's dumb enough to require you to use that, then this is how you do it, but you should never do it, is his opinion. But
well, yeah. I guess then, I mean, so I guess this, my question in a sense takes us outside of NMDS, but to you guys' knowledge, like, and would there be another tool that would give us a lot of the same benefits of NMDS, but that actually can partition variance along the axes? Like, you know, what's that?
Is this where like a Permanova would come in?
Well, that is maybe. But then you're saying things are significantly different, but not how much of the trend they explain, right?
Next week, I'm going to talk about a technique called partial least squares regression, which is a way to, so essentially you have a matrix of predictor variables, x's, and then a matrix of response variables, y's, and you basically perform kind of like a PCA on both of them separately, and so you reduce the dimensionality on both of those, and then you can correlate axes from both of those with each other. And so that's kind of one approach to that. I mean, I just like to make the point, and Nate was alluding to this, that a lot of these analyses, and no statistical analysis is perfect. Nate brought up a bunch of flaws with NMDS, even though it's a great, really great choice. There's still, stress considerations and whatnot. So unfortunately, I think still a lot of it is kind of eyeballing it and saying, well, this arrow points this direction and it's associated with this plots. You know what I mean?
Yeah. Well, yeah, thanks for that. I mean, yeah.
Yeah. From what I can tell, NMDS is like the pinnacle of not being able to explain the variance on the axes because of the way that the axes are created. Because they're kind of just, you randomly put these axes in and then just try to move the points around until you find the best configuration. So yeah, I've seen this guy Yariak Sanin talk about other ordinations, and he's not he's not fond of explaining variance on the axes for several of them. I think like PCA is great because that's kind of inherent to it. But for NMDS, yeah, he's not a fan, and I think it's one of those trade-off situations where you get a lot of use for community data out of NMDS. But yeah, definitely, it would be nice to know, like, is axis 2 and 3 important at all? Should I even be looking at that, or
Right. Yeah. Or like, if you're explaining so little of the variance anyway, then maybe talking about what explains what the patterns you saw isn't that important. But I guess we'll just wait till the next statistical genius comes along and helps us with that.
Yeah.
I really appreciate you guys doing this today. This was really enlightening. You guys went way deeper into the theory than I thought you would. So I personally really loved that. And I'm seeing lots of heads like bobbing in agreement. So all the Lucases are on board today. Cool. Any final comments from anybody for the guys? Questions?
Just a big thank you.
Yeah, this was super cool. Thanks for coming in.
Yeah, it's fun.
Yeah. So and David just alluded to teaching next week on partial least squares regression and Permanova. So 2 more tools that are going to be pretty useful to us. So I guess I need to hear from people now if you're just like, I'm freaking out. I need to just keep moving on my thing so that David doesn't, spend time preparing something that that we don't want, but I would listen to it myself. So I don't know if other people are feeling like that'll be useful. Okay. Yeah. Okay.
Yeah,
Awesome.
I would listen in.
Good. That's awesome. Great.
Yeah, I think Permanova would be great because Chime has that as like an automatic, well, not an automatic output, but it's one of the things you can do in Chime. And I could definitely use a refresher on like theory and what it's doing and what it tells you.
Totally.
So that'd be great.
Totally. Yeah.
Yeah, that sounds great. Thank you, guys.
David, do you have any, should we be, especially if we're not reading a paper for Monday, we may have a little bit more bandwidth if people want to read a paper on Permanova. Would we be going to like Marty Anderson's papers or a suggestion? Oh, you're muted somehow.
Sorry about that. Yeah, I mean, Anderson's paper is the one that explains it all, but to be completely honest, I'm going to go through a lot of the theory and what I hope is a clear way with a lot of graphical stuff. So I wouldn't worry too much about it. We can, if you guys have questions coding later, that may be the place to put the work in.
Okay, cool. Great. Well, we're off the